Okay, so in this session on statistical process control, I'll be discussing a few other aspects related to control charting, basic principles under control chart, and what is a control chart model. It's a generalized control chart model. The type 1 and type 2 errors in control charting. This is an important concept you must be aware of. Performance measures for a control chart, and particularly two kinds of the control chart or say performance measures we'll be using and we'll be referring to. One is operating characteristic curves, how to draw an operating characteristics curve for a control chart, and how to draw that average run length curves. So these are the two performance measures we are going to discuss. Now let us talk about a typical control chart model. So let me just go through certain points. Like let say theta represent a quality characteristics of interest, say length or diameter of a part, and theta hat represents an estimate of theta. Is it okay? That means you have to collect data, you have to measure the quality characteristics. For example, if theta is the mean diameter of parts produced by a process, theta hat would be the sample mean diameter of a set of parts chosen from the process. Is it okay? So obviously, the true mean is never known. That means the population mean may not be known. So what you try to do, that means from the population you collect the sample and the sample becomes a representative of the population, and then you measure individual values, you get the individual values or individual units related to the quality characteristics, and you have the sample values. So from the sample values you calculate the mean. So how many such samples you will consider? You will be considered several such samples. Is it okay? Because if you remember, when you refer to the control chart, you say that I will be plotting the sample values over the samples, and these samples are drawn maintaining the time order. Is it okay? So what is the expected value of theta hat? So it represents the mean or expected value, and against theta hat you have the several sample values. So obviously from the several samples values you can calculate its standard deviation. So the notation is sigma theta hat, standard deviation of the estimated theta hat. So how do you, what will be the expression for say central line? That is expected value of theta hat. Upper control limit is expected value plus k times this one, sigma of theta hat, and similarly the lower control limit is expected value of theta hat minus small k times sigma theta hat. So where small k represents the number of standard deviations of the sample statistic that the control limits are placed from the central line. Is it okay? So usually, unless otherwise stated, is it okay? Usually the value of k is assumed to be 3, and that's why many a time we refer to the control limits as plus minus 3 sigma limits, plus minus 3 sigma limits. Is it okay? So here is an example. A semi-automatic turret lathe machines the thickness of a part that is subsequently used in an assembly. So thickness is your basic quality characteristic of interest. The process mean is known to be 30 mm. This value is given to you with a standard deviation of 1.5 mm. That means this is also the process standard deviation or the population standard deviation. Construct a control chart for the average thickness using 3 sigma limits if samples of size 5 are randomly selected from the process. Okay, so this is your problem. So how do you get the solution? Control limit is known as 30 mm. Okay, this is the central line is 30 mm. The standard deviation of the sample mean as per the central limit theorem is sigma x bar equals to sigma upon root n. Is it okay? So this is 1.5 divided by root over 5, that is 0.671 mm. So what will be the upper control limit? That is 30 plus 3 times 0.671, that is 32.013, and the lower control limit is 30 minus 3 times 0.671, that is 27.987. Okay, so I think there is no problem in getting these ideas and in understanding these ideas. So this is the most simple problem, and we're assuming that control limits are at plus minus 3 sigma limits. Okay, so UCL is known, LCL is known. So now, you are trying to control the process, and the desirable condition that you ask for in a process, that is in control condition or in control state. And if the process remains in control state, that means process performance is guaranteed and the process becomes sustainable. Now, how to monitor the state of the process? Obviously, you are using one or more tools. One such tool that is commonly used, that is the control chart. Now, whenever you use certain kinds of tools or the control charts, while you make inferences about the state of the process, there is a chance that you will make some error, and this is known implicitly. Like say any tool techniques you use, obviously in majority of the cases you expect that there will not be error, but the error will be there, and it is your duty while you design a control chart related to a process, you design the control chart in such a way that these values of these errors should come down or should be minimum. Now, in respect of control charts, the two types of error you may commit while you try to make inferences about the state of the process. These two errors are type 1 error and type 2 error. So what is a type 1 error? Now the type 1 error means, the control chart shows that the process has gone out of control, and it is assumed. But when you actually verify your process, you may find that the process remains in control. So this is type 1 error. That means we are inferring that the process is out of control by looking at the control chart formation, but actually it is in control state. So the probability of a type 1 error is denoted by alpha. So at any point in time while you use a control chart, you must be in a position to calculate this type 1 error. Here, for example, you have the upper control limit and you have the lower control limit for say kind of chart, that is X bar chart. That's why it is written in the subscript. Okay, so that is UCL X bar, this is a central line, and you have LCL X bar. So now what you have plotted several values, and these values when the process is in control actually, so it shows a normal distribution. These are the values. Now out of all these values you have plotted, is it okay? This is the summary. What you find that the certain values are beyond upper control limit, whereas certain other values are beyond the lower control limit. And if it is normally distributed, then obviously there is the area under the curve, okay, beyond UCL and LCL. This is alpha by 2 plus alpha by 2, that means alpha. Is it okay? So it is a symmetric distribution. That's why these two areas are same. Okay, so this way, even if the process is in control, you will find that you can avoid these two areas. These are shown beyond upper control limit as well as the lower control limit. Is it okay? Less than. Okay, so this is the kind of error, and sometimes this type 1 error is also referred to as the false warning. Is it okay? That means unnecessarily you stop the process, you try to find out that is there any assignable cause or not, and you do not find any. So you say the process remains in control. Okay, but the second type of error, it becomes very, very critical in most cases, and this is type 2 error. So what is type 2 error? Type 2 error is, that means as per the control chart information, is it okay, you assume that the process is in control, but actually it has gone out of control. Is it okay? So obviously, it's if you assume, so that means you are unaware of assignable causes impacting the performance of the process, and at any point in time the process may stop functioning. So the type 1 error results from inferring that the process is in control when it is really out of control. So let us just look at this particular figure. This figure depicts a process going out of control due to a change in the process mean from A to B. Okay, so when you look at a particular control chart, actually the central line is indicative of that the process is under control and should be under control around this central line. Is it okay? So now what has happened, that the process was in control around A. That means the values will be plotted like this. What has happened, that due to some reasons, that there is a shift in the value of A, and it's a permanent shift, suppose. That means now the process is working definitely, but the value of A has now become value of B. So this is an upward shift. Is it okay? So now the entire process has shifted around this, but you still are using the same control chart. And what you find, that this process actually has gone out of control. Is it okay? But this is the area, that means this area, that means lower control limit and the upper control limit, is entire area. That means this is the probability. It shows that this is the probability that you assume that the process is in control. So the process mean has shifted from A to B. For this situation, the correct conclusion is that the process is out of control, but that you cannot do. Obviously, you have not changed your control chart with respect to B. There is a strong possibility of the sample statistics falling within the control limits. That means this is the area. That means many such points, is it okay, majority of the points will still fall in this particular zone. So we would conclude that the process is in control and thus make a type 2 error. So there is a high probability. So your system should be such that you must be able to detect the type 2 error as quickly as possible. It is unavoidable, but make sure that you are prompt enough and you are sensitive enough, and you have mechanism with you with which you will be able to detect the occurrence of type 2 error, and you will be in a position to bring back the process from an out of control state to an in control state. So here is an example. I will just quickly go through this example. A control chart is to be constructed for the average baking strength of nylon fibers. Samples of size 5 are randomly chosen from the process. Okay, so this is you have to do. The process mean and the standard deviation are estimated to be 120 kg and 8 kg respectively. right? So these are known. So these two values are given. So we are assuming that the control limits that do exist at plus minus 3 sigma limits from the mean. What is the probability of a type 1 error? So what do? That means you know what is the upper control limit. So we have already determined this is the upper control limit, and this is the the process mean, and this is basically the sample standard deviation, and the sample standard deviation is given by sigma x bar is equals to sigma upon root n as per central limit theorem. So what is central limit theorem? Central limit theorem says that whatever may be the distribution of x, the distribution of any statistic of x, say x bar, is it okay, is approximately normal when the sample size is very large. Is it okay? So we are assuming at this stage that the central limit theorem, central limit theorem is applicable, and so the normality assumption holds. So the z values at the lower control limit. So this is at the upper control limit, that is 130.733. So we have computed the upper control limit and corresponding z value we have computed. Is it okay? That means difference from the mean, that is 120, and expressed in the standard deviation units, that is 3. Similarly, if you compute the z value at the lower control limit, you get a value of minus 3. So these z values in the standard normal table, each tail area is found to be 0.0013. Is it okay? So the probability of a type 1 error is therefore 0.0026. Clear? So you should remember these values. That means in many a time you come across a situation where control limits are at plus minus 3 sigma limits, and you assume that the normality assumption is valid. Okay, so hence you should remember this one. Okay, that is the probability of making type 1 error, that is 0.0026. Now, if the process mean shifts to 120 kg, how do you compute the type 2 error? It's clear. That means previously it was 120, now it has become say 125. Is it okay? So this is upper control limit we have already determined 130.733, lower control limit is 109.267, is right. So this is the area alpha by 2, that is 0.0013. The process is in control around 120, and this is on the other side 0.0013. So if you add these two, alpha by 2 plus alpha by 2, so it becomes 0.0026. Okay. So how to compute the probability of making type 2 error? So now initially it was 120. Okay, the process the central the value, the mean of the process is 120. Now it has shifted 125. Is it okay? So but the old the control chart is still using, and so what you find that this process has shifted around 125. Is it okay? So what you find that you need to compute this area, that is the probability of making, is it okay, type, no, this is the probability of making, say, right conclusions actually. So this area is shown as out of control. Is it okay? Similarly, this area is also shown as out of control, whereas the area between this and this, within this, they are still shown within the say upper control limit and lower control limit. So this area you must know. So how do you do this? So it's very simple. That means area, that means z value around say z value at 130.733 when the mu is 125. So that you calculate, and we are assuming the sigma remains same, and you calculate the z value at 109.267 when the mean is shifted to 125. Is it okay? So this calculation you do, that means the z1 at 130.733, the changed mean value is 125, whereas we are assuming that the standard deviation doesn't change. But just make a note that usually, both the values, may change, and we may assume that the sigma and the mu, they are in many a time they are related. Is it okay? Whereas right now we are assuming that the sigma is not related to mu. Is it okay? So this is just a first approximation. So this value is against 130.733. Now it has become 1.60, and Z value at 109.267. Is it okay? That is the lower control limit. At when mu is changed to 125, this has become minus 4.40. So from the now you refer to the standard normal table. What you find that the tail area above the upper control limit is 0.0548, and the tail area below the lower control limit, that is when this age is almost 0. That means up to 4 decimal place it is 0. So the area between the control limits is 1 minus this plus this, that means 0.9452. That means what is your type 2 error probability? That is 0.9452. That means in 94.52% of the cases, you will be unable to detect this shift, the shift from 120 to 125. That means though the process has gone out of control, in 94.5% of the cases, you will assume that the process remains in control. So you will be making type 2 error. What is the probability of detecting the shift by the second sample plotted after the shift if the samples are chosen independently? What we are assuming at this stage, when you are going to plot all these sample points, we are assuming just the point to be noted that all these sample points are independent with one another. That means no way one single the sample point influences the other the sample points or the sample values. So how do you get an answer to this question? The probability of detecting the shift by the second sample is the probability that detecting the shift on the sample 1, that is the first event. Second event is your probability that you are not detecting the shift in the sample 1, but you are detecting the shift in sample 2 is obviously. So the first probability is 0.0548, the second probability is 1 minus 0.0548 into 0.0548, that is 0.0518, assuming independence of the two samples. So this is to be noted, right? Means we are assuming that all the sample points are independent with one another. So the total probability is this one, that is 0.1066. That means 10.66%. Okay, so this is a typical problem we come across, and instead of having say here by the second sample, so you may compute the what is the probability that this is detected by say the third sample or by fourth sample by nth sample. Is it okay? So now we'll be just referring to the two types of performance measures which are usually used against a control chart. That means you are using a control chart, and obviously there is a chance that you will be making type 2 error. Now at certain point in time, while you use the control chart, you must be able to assess your performance, whether your control chart's performance is acceptable to you or not. So for that, two kinds of the performance measures we recommend. The first one is the operating characteristics curves that you have to draw, and the second one is average run length and average run length curve. Is it okay? So I am going to discuss first the operating characteristic curve. What is then an operating characteristic curve? It is a measure of goodness of a control chart's ability to detect changes in the process parameters. So essentially it is a plot of beta versus the process parameter values. Okay, and that parameter depends on which kind of control chart you use. Okay, so if you use a P control chart, later on we'll come to know there are different types of control charts you use under the different situations, so the different conditions we'll explain in detail. So against a particular control chart, you must know what is the process parameter, and you also must know what are the possible process parameter values, and against each process parameter value you select, you must be able to determine say the probability of making type 2 error. Like in the previous examples, we say that initially the process mean was 120, so that means that is a particular value of the process parameter. Now it changes to 125. So when it changes to 125, we have computed so what is the probability of making type 2 error. So this is just one computation. This process parameter may assume other values like say 130, 140, 135 and so on. So against all such possible values, okay, which a process may have, okay, due to various reasons, what is the corresponding probability of making type 2 error? So this is just an example we are giving. So this way we get the different values of beta, and beta values are plotted against several values of theta. So like say here, the process mean, there are so many the process mean values we have assumed, and against a particular process mean, we can compute the Z value and average the area above UCL, area below LCL, probability of non-detection of the shift in the process parameter value. That way we define the probability of making type 2 error. So this is your beta value. Similarly, suppose it is 127.56. So corresponding value at that is Z1 is 1 against that particular control chart which you use. Is it okay? So for which the upper control limit and the lower control limit is determined. So Z value at upper control limit, that is 1. So area above upper control limit is 0.1587, and Z value at LCL is -5. So this is 0. So the area between upper control limit and lower control limit will be 0.8413. So this way, for several values of process mean considered, you calculate the corresponding values of beta, and next you plot them. So that means here we are assuming that these are the possible values, like say 123, 128, 133, 138. These are the possible values. That means these values are technically feasible for the process parameters. And suppose the control chart is drawn over there at 120. Is it okay? So that is the base. So what we are assuming, that is the positive shift. Is it okay? There could be negative shift also, but we are just showing that how to draw the operating characteristics curves. Okay, so we are the positive deviation we have considered, possible deviations. So if you look at this figure, what you will find that as the shift magnitude changes, is it okay, either on the positive side or on the negative side, what you will find that the probability of non-detection decreases. But if the shift magnitude is very, very small, is it okay? So this is one of the characteristics of a typical Schwartz control chart. That means when the shift is small, the probability of its detection is not that high. But obviously, if the shift magnitude is substantial, the probability of non-detection comes down. Okay, so this is a typical one. The next one is the important the performance measures. Many a time we recommend, that is the average run length. Now, what is the average run length? Average run length is defined as the number of samples on an average that you require to detect an out of control state or signal. I repeat, that means average run length is, so you start using a control chart. At any point in time, the process may go out of control. So and you are basing your decision on the sample values, and you are comparing the sample values with the upper control limit or the lower control limit. So how many, if the process goes out of control, how many the sample points you are required to plot before you will be able to detect this condition, out of control condition. So supposing PD denotes the probability of an observation plotting outside the control limits, that is the probability. Okay. So the run length is 1 with the probability of PD. Is it okay? That means you plot this point. What is the probability that this point will be plotted beyond upper control limit or beyond lower control limit? That is the PD. So it will be 1. If it is 2, that means the first point when you plot, is it okay? It is not detected as an out of control point, but the second point definitely, and that's why the run length is 2. It could be 3, that means the first 2 sample the points, is it okay? They are not shown as out of control point, but the third one is shown as an out of control point. So corresponding probability is this. So average or the expected value of run length, how do you calculate? That means the general formulation is sigma z equals to 1 to infinity z into 1 minus PD to the power j minus 1 into PD. Is it okay? And it is the convergent infinite series. So obviously, the ARL ultimately becomes 1 upon PD. So this is the most simple formula. Now, you always come across 2 situations as far as the process condition is concerned. The first condition is the case 1, when the process is in control and control limits are at plus minus 3 sigma limits. This is a very common occurrence. In fact, the process is in control. So what is the value of ARL? ARL is obviously 1 upon alpha. So alpha is 0.0026. So that means it is 385. That means on an average, every after 385, okay, the sample points are going to plot, those 385th point may be shown as an out of control point. Clear? The next case is when the process is out of control. Is it okay? There could be many reasons. There are there are many reasons you will come to know later on. So what will be the expressions for ARL? ARL is 1 upon 1 minus beta. So what is beta? Beta is the probability of detection of the shift. And what is 1 minus beta? That means the probability of 1 minus beta is the probability of detection, and beta is probability of non-detection. So, and the beta is the probability of type 2 error. So ARL should be as minimum as possible, say 4 to 4 or 5. So when the process goes out of control, that means you must know that what is the probability of making type 2 error. That means probability of non-detection. So ARL curves for control charts for the mean is a graph with ARL versus change value of the process mean. Now here what we conclude, that means sometimes what you do, you give the warning limits. Is it okay? And these are actually the placed at plus minus 2 sigma from the center line. Okay, is it okay? That means in order to have an online real-time control, you must place the warning limits also. Is it okay? So now the basic issue is that the process may be in control or process may go out of control. So if the process is in control, is it okay? You try to know that what are the reasons that why what is specifically related to a process. So you must be aware of the process settings and to what extent you relate the process condition or the state of the process with the process settings. Okay, this is first part. The second part is that at any point in time the process may go out of control. So immediately the first thing you have to do, that means how quickly you are able to detect this condition, and if you are able to detect the conditions, you must be able to identify the assignable causes, and then you have to take some the corrective measures at the first stage, and later on you have to take some preventive measures. So whenever someone starts using the control chart process, we are assuming that he believes in the concept of prevention based quality control. Okay, so other aspects we will discuss in the subsequent lecture classes.